So for our third question, we have to start with the boundary layer condition, and we have to derive we have to come up with an ordinary differential equation to represent the flow over a wedge. So for the wedge is shown with an angle of beta, and the u infinity initially is this, and after some time it would be with a boundary layer growth, it would be something this. And so for so we will represent the initial velocity by a stream function. So for the stream function phi, we would have del square by phi equal to 0, and the boundary condition initial would be the u theta would be 0 at theta is equal to beta and theta is equal to pi minus beta, because the velocity along the wedge would be 0. So if and for this problem we would choose the polar coordinate. So we will write ur as del psi by del r and u theta as 1 by r del psi by del theta. So now writing the continuity equation, now writing the mass conservation equation. So we will have del r plus 1 by r square del square phi by del theta equal to 0. I have replaces the ur and u theta in the moment in the mass conservation equation. So this will give us r del by del r del psi by del r plus del square phi by del theta square equal to 0. So if we want to separate the variables, let us assume the stream function to be some capital R, which is a function of small r, and some capital theta, which is a function of small theta. And if we replace this in the continuity equation, we will have and we can write this equation simplifying del by del r del r by small del r is equal to minus 1 upon theta capital theta del square capital theta by del theta square, and say this is equal to some lambda square, some constant square. And we can see that this is a differential equation only in r, and this is only in theta. So we can solve them simultaneously to have the function of r and small r and in capital theta and small theta. So we can write the differential equation as del square theta by del theta square, this is capital theta, plus lambda square theta is equal to 0, and r square del square r by del r square plus r del r by del r minus lambda square r equal to 0, capital R equal to 0. So for the theta, what we will get? So theta would simply be just a sin theta plus b cos theta, because it's an simple harmonic motion equation, and with the boundary condition that theta equal to 0 at theta equal to 0, we have u theta equal to 0, which is capital theta. So we have theta simply as a cos. One more thing here, lambda would come because lambda is the frequency here. So here lambda would come, and for the r, if we replace by some c1 e to the power lambda r. We will have capital R as c1 r to the power minus lambda. So for the final expression of psi, we have simply c1 r to the power lambda cos theta. This is the stream function that we are getting, and we can write u theta as 1 by r del psi by del theta, which will give us minus lambda c1 r lambda minus 1 sine of lambda theta. Again I make the mistake here, it would be cos of lambda theta. Okay, so u theta is this, and u theta is this, and by using that at theta equal to 0, we will have u theta equal to 0, which will give us what it will give us. It will give us sine of lambda pi minus beta equal to 0, and so we would have lambda is equal to n pi upon pi minus b, and for like if n equal to 1, we will have lambda as pi upon pi minus b, pi minus beta. So simply writing ur as del psi by del r, we will have the expression minus c1 lambda r lambda minus 1 sine lambda theta. So again at theta equal to 0, we have ur is equal to u infinity at the previous x, this. So by equating it, we have u infinity is minus c1 lambda x to the power lambda minus 1 I did some mistake here, I don't know. Del psi by del r. Yes, so it would not be sine lambda theta, it would be cos lambda theta, because phi is this, and the differentiation would bring only the lambda here and r lambda minus 1, so the theta would be 0. So we have the expression of u infinity. So what we can say, so let us say that lambda minus 1 is m, so we can write u infinity some a constant x to the power m. So we have come up with the expression of u infinity also. Okay, so now writing the x momentum equation, what we will have is, if we consider the flow to be steady, so we will have ux plus vuy is minus 1 upon rho px plus nu uyy. Okay, and now if we see this momentum equation at y tending to infinity, at y tending to infinity, we would have the boundary condition u is going to u infinity, and so del u by del y would be going to 0. So similarly del 2 uy by del y square will also be going to 0. So if we replace it in the momentum equation, we will have u infinity del u infinity by del x is minus 1 upon rho del p by del x. Okay, this is also an important result that we will use. Okay, and so now we can from the Blazier's equation, we can write the solution psi as u infinity x delta of x f of neta, where we are seeking the similarity solution in neta, which is neta is y by delta. Delta represent the growth of the boundary layer as we move in the x direction, and the function and the stream function that captures the solution is this. And so yes, so if we want to write it again, so we will have u as del psi by del y and v as minus del psi by del x. And if we do this, what we will have is u would be simply u infinity delta f dash 1 upon delta. Okay, so it would be u infinity f dash. So u we have got. Similarly, del u by del y would be simply u infinity f dash by delta, and del 2 u by del y square would be u infinity delta square f double dot. Okay, so we have found u, and so now we will go towards, okay, let us found del u by del x also. So it would be u infinity delta f dash u infinity f dash delta, and it would be minus 1 upon delta square del delta by del x plus u infinity f del delta by del x plus u infinity plus f delta and del u infinity by del x. Okay, so if we simplify the expression, what we will have is finally is minus u infinity by delta, just a minute. Yes, so this I wrote wrong because I differentiated the function psi instead of u. So it would be actually del u by del x would be del by del x of u infinity and f dash. Okay, so it's easy now. So it would be u infinity f double dash then del f double dash, and it would be del by del x of y by delta plus f dash del u infinity by del x. Okay, so the expression of u, we can del u by del x we can write as minus u infinity delta f double dash delta del by del x plus f dash del u infinity by del x. So now only v is remaining, so v is basically minus of del psi by del x, and which would give us what it would give us. It would give us, let us differentiate del psi by del x, so minus beta 1 minus is outside also, f dash u infinity del delta by del x plus f del by del x u infinity delta. Okay, so now if we replace all the variables in the equation, u del u by del x plus v del u by del y is minus 1 upon rho del p by del x plus nu del 2 u by del y square. So this would be replaced by u infinity del u infinity by del x. So what eventually we will have is u infinity f dash del u infinity by del x f dash plus u infinity f dash u infinity f double dash minus neta by delta del delta by del x, and again minus 1 upon delta what would come, yes, neta f dash u infinity del delta by del x plus f del by del x of u infinity f u infinity, what is here, f dash infinity which would be equal to u infinity del u infinity by del x plus nu u infinity f triple dash 1 upon delta square. So if we take the terms common and then subtract, what we will left with is u infinity del u infinity by, like if we see that u infinity f dash is common here and here, and again neta, and this term would cancel with this term. So what we will see is f double dash minus u infinity by delta del by del x of u infinity delta ff double dash is equal to u infinity del u infinity by del x plus mu u infinity by delta square f triple dash. Okay, so if we simplify the equation further, what we will have is f triple dash plus f dash f double dash f dash delta square by nu del u infinity by del x plus u infinity by delta del of delta by del x plus delta square by nu del u infinity by del x 1 minus f dash whole square is equal to 0. Okay, so if we write what we write, if we express this as alpha 1 and this as alpha 2, what we would finally have is f triple dash plus let us say alpha 1 f double dash plus alpha 2 1 minus f dash whole square equal to 0. So what we have alpha 1 as delta by nu del by del x of u infinity delta, and we have alpha 2 as delta square by nu del u infinity by del x. Simple. Okay, so to arrive at the expression what the question is demanding from us, we have to take alpha 2, which is equal to delta square by nu, and am x minus 1 as 2m m plus 1. Okay, and so from here we can simply have the expression of delta as nu alpha 2, not alpha 2, nu 2m m plus 1, sorry, m would be cancelled out, and it would be 2 nu m plus 1 x to the power m minus 1 to the power 1 by 2, and I think in a better way it would be 2 nu m plus 1 x to the power 1 minus m to the power 1 by 2. Okay, so if we now simplify the expression for alpha 1, it would be delta by nu del by del x of u infinity delta, which would be delta by nu u infinity del of delta by del x plus delta del by del x of u infinity. And now if we replace the terms here, what we will have is we will have 2m m plus 1 plus u infinity by nu del by del x of delta square by 2, which on further simplification gives us 2m m plus 1 plus ax to the power m for u infinity nu, and if we do the differentiation of delta square by 2, it would be like delta square by 2 would be simply this, so it would be nu 1 plus m. What would come? 1 minus m would come, and x to the power m, so it would be 2m and m plus 1 and 1 plus 1 minus m upon what it would be, simply 2m. It would give us 1. So if we have alpha 2 as 2m m plus 1, we found that alpha 1 is 1. So the final equation that we arrived is f double dash plus f double dash plus alpha 2m m plus 1 1 minus f dash whole square equal to 0. So this is the final expression that we have. So now for the boundary conditions, what we have to do is, for the boundary conditions, we simply have at y equal to 0, we will have we have neta equal to 0. So we have f of 0 is simply f dash 0, which is equal to 0, and as y tending to infinity, we will have u tending to u infinity. So this will give us f dash neta tending to infinity as 1. So this is done.